Да, у нас тут лекция. Есть звук, да? Ну, разброс высокий, коммутативная алгебра, алгебраическая геометрия. Хотите теорию вариантов, хотите теорию представлений, хотите представления этих ассоциативных алгебр, каких-нибудь бесконечномерных.
А что-нибудь с топологией связано, например?
Алгебраическая топология нет, это не то, что меня интересует. Угу. Okay, so today we continue and we have a chances to finish the chapter about the filtered and graded rings. So if I remember correctly, last time we finished with the following observation that we can consider maps of modules. So you can say that there is a map of modules between m to some n shifted by some degree d, and this is we call it the map of degree d, right? If this preserves the degrees, then you just don't write anything. This is shifted by 0. So can you give me an example, say specifically of the degree d map for any d?
Well, k of x goes to k of x to k of x, and x goes to x power d.
Yeah. So examples. So in the first example, well, let's take a ring to be the same as the module, so m and n, and in this case just a polynomial ring in one variable. Say we assume that the degree of x is equal to 1. So then we can consider the following map. So let me just say f is a map from the r to the r shifted by d. And this is the map that is multiplication on, so I multiply on the x to the d. And this of course works for any d greater or equal than 0. So it won't work for negative d because, well, this element is not in the ring. And you can think in this case that we discussed at the end that there are many free modules depending on where you put generators. So this is a free module where you put generator in degree 0, this is a free module where you put generator in degree d, and you can think about this as a 1-by-1 matrix representing a map between two free modules. In general, if you consider, well, what's a free module? Oh, say this is true, and say any free module so this will be a sum of r, and then you have some shifts. So maybe let's write, well, you can, sometimes people say minus j, sometimes it's just j. So this will be some, and even it's possible that for a fixed degree, there are several generators in this fixed degree, so in degree j. So potentially I need to write some power, so let me call this beta j. And the summation is over j. So any free module would look like this. And if you want to understand the home module, say home, and this is a, say, graded module, so say, let's take a component of degree 0, since all other components are just shifts of this of the second argument. So what if you want to understand home, so all the maps of degree 0 between one free module that I'm going to write like this, and some other free module. Well, I don't really want to call this different letter because this is standard convention. When you study graded resolutions, there will be several such modules depending on what degree you consider in the resolution. So there will be two indices, and this beta are called Betty tables of a module. So this is why I want to use this notation. So, but anyway, so the thing I want to say here is that you know that if you have just a ring, two free modules, and you want to understand homomorphism between two free modules, say a finite ring. So let's suppose that this is a finite sum and this is a finite sum. So then there is a very precise description of all the maps. This is just a rectangular matrices with elements in R. So here is also rectangular matrices, but of course you have more restrictions since you're supposed to preserve the degree. And do you see what's supposed to be the restriction here on the matrix? So not any matrix work as a module in this home space.
Probably matrix should be square.
No, a square matrix, it just means that we have the same number of generators here and here. This is why when you get a square matrix. Yeah, so at least you need to say that all the elements in the matrix are homogeneous elements. So let me just say that, say maybe elements of this home space are matrices with homogeneous elements. So let me give you even more precise example. So 3, continue to assume that R.
Can you explain why this should be homogeneous elements?
You're going to see in the example, then from this example probably it's very easy to generalize. So in this case, I still take a polynomial ring in one variable. Now let me start with the matrix. Suppose I want to consider matrix. Well, if we want to matrix with the homogeneous elements, so let's say x squared, x cubed, x to the 4. So this is the matrix. So I want to interpret this matrix as a map between two free modules. So of course this is not a kind of canonical way. There are choices. Of course you can, whenever you have a map like this, you can shift the m and shift the n by some integer, and it's still represented by the same matrix. So the map, so modules that I want to choose are not canonical, but at least this works. For example, if I, well, I can, well, let's say that I start with R, then I shift this by the -1, take a direct sum, shift this by the -2. So suppose I want to consider this module, and if I take a couple of elements, so when I multiply, well, how we multiply? Row on the column, so the column is just these two elements from first component here, second component is here. So when I do multiplication on x, I increase the degree by 1. And then I, x squared, increase the degree by 2. So when I compute the first component of the answer, I'll get something in the R, right?
Yes.
So then there will be a second direct sum for the second component. But here I again start with something in the -1, increase by 3. Yeah, so here the second component is R shifted by 2.
Okay, well, what would be like if there will be x cubed, there will be R.
Here?
Yeah.
Well, then it would be a matrix with homogeneous elements, which is not a map between two free modules.
So it's not only this should be homogeneous elements, it should be also, I don't know, something like...
Well, there has to be some specific relations between the degrees of these homogeneous elements, since you see, for example, here, or you can start, for example, with any row and interpret this as a map between two.
I think like column should be, like the first column is, as the second column, it's just first column multiplied by x. So it should be something like that, yeah?
Yeah, so the shift in the degrees in the columns have to be the same.
Okay.
So for example, if I put shift here shifted by 1, here also shifted by 1, if I put x to the 5, I can't interpret this as a map between two free modules. So this is the kind of canonical independent of the basis space. But of course, if, well, you know that the elements are matrices with homogeneous elements, but not any matrix with homogeneous elements is an element in this space. If you want, well, you said already the answer, you can compute the degrees of these homogeneous elements in terms of the betas. Okay, so these are examples of the homomorphisms. Dun, dun, dun. Well, now I have a kind of a little bit boring several observations that I'm not going to prove. So I'll start with the definition and then I formulate a couple of propositions, and we postpone the proofs until we have seminar on graded modules. So a submodule n in the module M is called graded if the inclusion map preserves the degree. And okay, so say this is the first part definition, and of course we can define homogeneous ideal I in some graded ring R. Well, is a submodule, is a graded submodule. This is definition. Well, you can say that this is homogeneous ideal. You can say this is graded ideal. That's also possible terminology. Homogeneous or graded ideal. Well, this is just a submodule in the sense of the previous part of the definition. So here I have a characterization of the submodules. So proposition, the following are equivalent. So this is what I want to postpone to the seminars. So I have a submodule. So the following conditions for the submodule are equivalent. So the first condition, n is graded submodule. In other words, this definition is satisfied. So part 2, if you consider component ni, this is the intersection of the n and mi. So of course this is for all integers, and in this case n is the direct sum of its components. Condition 3, n is generated by homogeneous elements. And condition 4, if we have element x, I can consider this element as an element in M. As an element in M, it has homogeneous components. So these homogeneous components are supposed to be all in N. And then all its homogeneous components are in N. So proof is exercise. But we can illustrate this with some examples. So, for example, 1. Let's restrict our attention where M is a ring and N is an ideal. So, for example, I take ideal generated, say, by the x squared and y squared that sits inside of the polynomial ring into variables. And for simplicity, let's assume that the degree of x is the same as the degree of y and just equal to 1. Well, clearly this is homogeneous. For example, you can use property 3, generated by generated by the two elements, and the two elements are homogeneous. So I is homogeneous or graded ideal. So 2, well, if you consider, for example, x cubed minus y squared inside the same polynomial ring with the same degrees. Well, clearly this is not homogeneous. That's not homogeneous element. So then I is not homogeneous.
So in graded rings, there's like type of ideals. Can be homogeneous, can be not.
Well, if you work with something graded, so you see grading on your ring, and then you probably want to work with graded modules, graded submodules, graded ideals. So you want everything to be graded.
So it's just not useful if it's not homogeneous.
Well, if it's not homogeneous, essentially, well, you don't use the grading, so you just use the standard ring theory that we developed so far. So the reason why it's useful when you have something graded, usually, well, you want to have something like the graded components are finite dimensional. Say, for example, A0 is just a vector space. All the components in the algebra are finite dimensional vector spaces. And then the graded ring, which will be very well infinitely dimensional, but if each component is finite dimensional, well, sometimes you can use some methods that, say, work for finite dimensional algebras for graded situation. So we're going to return to this later. But in these examples, I also wanted to give kind of canonical example. Let's call this example 3. So here, if you have any graded, so it looks like last time I was using A for the notation, now I'm using R. Well, but that's the same thing. So let's suppose that I still have this A, which is the sum over all non-negative I, components AI. So then there is a canonical ideal which we have in any graded algebra or graded ring. So we just take the A plus, which will be the sum of I which are positive. And this is always a graded ideal, so a homogeneous ideal. So then, of course, there is a very straightforward exercise, or maybe let's formulate this as an exercise. So if n inside M is a graded submodule, so then the quotient is the graded module. And again, let's do examples. So if you take a quotient of the A by the A plus, well, clearly you're getting just A0, which is of course graded, but the grading is not very interesting, that everything sits in 1 degree. So then you can do some non-commutative examples. So you know that there is a tensor algebra of a module. So you can take T of M, which should be just the direct sum of all non-negative i's, M to the tensor power I. Right? We discussed this a little bit in the beginning of the course. So this is a version of non-commutative polynomials. No, well, if at least when M is a free module, you can say that this is a version of non-commutative polynomials over some ring R. So this is over R, and R is not necessarily graded. So then from this tensor algebra, you can produce at least 2 other graded algebras. You can produce the symmetric algebra of a module, this is the quotient of the tensor algebra of a module, modular some relations, well, relations that you want to have is something like two-sided ideal generated by the, say, x tensor y minus y tensor x.
I mean like symmetric.
Yeah, symmetric algebra.
Yes, symmetric.
And what's important here, notice that all the generators are of degree 2. And since all the generators are homogeneous, this is a graded ideal. Of course, in this case, this is not a commutative situation, but the same works. So the algebra is not commutative, but the ideal is homogeneous, and the quotient is a graded algebra.
And ideal generated by this is homogeneous because the both parts.
Yeah, because here this is of degree 2 and degree 2. Yeah, and I'm taking two-sided ideal, meaning that I have tensors in this ideal. I have tensors where I have this expression, and I can multiply on any tensor on the left and any tensor on the right. And then there is, of course, the situation with the exterior algebra of a module, which is also a quotient of a graded algebra, which is tensor algebra by some graded ideal. And in this case, well, I think it's enough to consider ideals x tensor x. So x squared is equal to 0 in this quotient. And then we can, for example, consider element x plus y, its square is 0, so we get the standard supercommutativity property of the exterior algebra. So this is not completely commutative situation. You start with something commutative. Here in this case you get graded algebra which is commutative. In this case you get a graded algebra which is supercommutative. So meaning that the standard identity xy is equal to the yx. Now here, well, this is not true, but what is true that xy is equal to the 1 minus of degree x degree y yx. So when I have this additional signs, I usually say this is super something. So this is supercommutativity. Okay. So next proposition. Again, the following are equivalent. Now I have only two properties. So the first property that A is Noetherian, and 2 is the following. A0 is Noetherian, so A0 is Noetherian, and A is an algebra of finite type. Over A0. And also notice that, for example, if you still want to be in the commutative ring situation, here the example of the symmetric algebra of some module give you an example of the graded algebra where A0 is just any ring that you want. So the zeroth component here is just any ring R, any commutative ring that you want. So proof. Okay. First suppose that, yeah, we suppose that A is Noetherian from 1 to 2. So then, of course, we automatically get that A0 is Noetherian, since this is just a quotient, right? We have it here. So A0 is a quotient. Oh, this is summoned as an abelian group. So I would rather say that since A is Noetherian, any quotient of Noetherian is Noetherian, so A0 is Noetherian. So then we have this first part of the 2. Now we want to say that this is an algebra of finite type. Okay, let's now look at the A plus. Oh, sometimes, especially in algebraic geometry, people say that this A plus is the irrelevant ideal. So this corresponds, for example, if you take a polynomial ring, you take the irrelevant ideal, this is the something that corresponds to the origin. And for example, if you construct a projective space, when you construct a projective space, you remove the origin from the affine space and then consider some equivalence relation. In algebraic geometry, that would be graded prime ideals, but still something that you want to remove. So hence the name. So in this case, A plus, well, that's an ideal in the A, and A is Noetherian, right? So I can say that this is finitely generated. So let's call the generators x1 up to xs. So this is finitely generated ideal since we have a Noetherian ring. And we also know that this is a graded ideal, so we can as well fix the degrees of these generators. So let's say the degree of the xi is the number ki, some positive integer. Then we consider A prime, and this will be by definition the algebra generated over A0 by the x1 xs. Notice this is not the polynomial algebra. Yeah, I'm just writing all the elements that I can generate using K0 and these elements. So the claim is, of course, that this is clearly an algebra of finite type by construction. So the claim is that the A prime is the same as A. So if we can prove this, then we're done. So of course, by construction again, this sits inside the given algebra A. So we only need to show that actually they coincide. And this is done by induction. So by induction on n. So by induction on n, we want to show that an n is the degree of the homogeneous component of the given algebra. So an, by induction on n, we want to show that an is inside A prime. So if we can do this, well, that's the end of the proof. Well, the base of the induction is clear, of course. A0 is inside A prime. Now, let's take some y in the yn. So I claim that I can take this element y and decompose this. Well, now this is not the base, so this n is greater or equal than 1. So this element y is in this ideal. And hence this element is in the ideal. I can write this in terms of the generators of the ideal. So let's say that I have a some coefficients ai, xi, I is running between 1 and s. So y is the homogeneous element of degree n. So without loss of generality, since these xi's are also homogeneous of some degree ki, I can assume that the coefficients that I have here, so ai, lives in the degree a n minus ki. Right? But that's the end of the proof, actually. Since we know that all the coefficients has degrees smaller than n, so then they are already in the A prime. So all the elements xi are in the A prime by construction. So this sum of products is in the A prime. So now I need to write this on the whiteboard. So since these ki's are greater than 0, ai's are in the A prime by the induction hypothesis, so y is in the A prime. So of course I need to say this is for any I between 1 and s, etc. Okay. So next section in this chapter, 8.2, stable filtrations. So let me just mention briefly that in general you have graded rings. You can also define filtered rings and filtered modules. So if, for example, you start with a ring R, so then inside this ring R you get a filtration. So let me call this F0R, and then you have F1R, and then you just continue. A priori that's an infinite filtration. Maybe you want F0 to be equal. So F0R is just the same thing as R, and you have some small abelian subgroups. And of course the condition would be the standard that Fi R, if you multiply this Fjr, is supposed to be something in the Fi plus Jr. Ah, yeah, thank you. Yeah, so we proved 1 to 2, right? So now 2 to 4, this follows by the Hilbert's basis theorem. So this is so easy that I forget to mention this. Yeah, so in the other direction, that's a trivial observation. So if you have this just immediately follows from the Hilbert's basis theorem. Yeah, so I was saying that you can define these filtrations in general, and then you can do this for modules. So you start with some module over R. You have abelian subgroup of F0 M supposed to be the same as M. Then inside this sitting M, F1 of M, etc. And then there is a condition that when you multiply Fi R on some element in the Fjm, this is something in the Fi plus Jm. So pretty straightforward definitions, but we're not going to use this and develop this other theory. So instead I have different plans. My plan is to define a very special kind of filtrations associated with ideals and use them as the tools to prove something about ideals. So essentially, if you want to work with this definition, so this is for rings, the filtration that I want to consider for rings is the following. So F k R is I to the k, where I is some fixed ideal. So any ring, commutative ring, is filtered by powers of some ideal, where by definition you say that 0's power of the ideal is just equal to the ring. So if you want to think in terms of this definition, this is the filtration I'm using, but now I can just give a kind of independent definition. So fix an ideal in the ring, and M is our module. So first, M is called filtered if there is a decreasing chain like this. So M0 is equal to M, then inside there is M1, there is M2, etc. Now potentially, of course, it is possible that the filtration is completely trivial, so you have only, all the components are the same, so you can write it like this. And it's also true in the previous couple of definitions. So we called it M is filtered if there is chain, here is the chain of submodules. In fact, we've seen already filtrations when we discussed the modules of finite length. It was given kind of in terms of filtration. The definition was in terms of filtration. It's also a prime filtration over for any finite module of a Noetherian, say or for any Noetherian module. So part 2 of the definition.
Is there no filtered models? Like the definition is kind of strange. If exists chain, well, I can construct chain for any model, like just M.
Sure, you can do this.
So any model is filtered.
Well, in this sense, any ring is graded because you can put everything in degree 0.
Okay.
So this first part is not a very interesting part of the definition. So this is not enough information here. For example, I haven't used ideal yet.
Yeah.
So it will come in the part 2 and 3.
Okay. So is module called filters if we're kind of given this chain and we fix it? Yeah?
Yes. So the filtered module is a module plus filtration. So filtration is this chain. Yeah, but again, don't take this very seriously. That's just a preparation for the interesting part of the definition. So filtration is called I-filtration if we have additional condition for these submodules. So Mn sits inside M with index n plus 1, and this is for any positive, non-negative n.
And there, and then is from filtration.
Yeah, so this is from so we take a module, we take a chain of submodules, and we put additional condition. So condition definition 3. So an I-filtration is called stable if we have one more condition. So Mn is the same thing as the M n plus 1, but this is for all n greater or equal than some n0. So for sufficiently high numbers n, they actually the same. So there is a kind of this stabilization of the filtration for sufficiently high n. So example. So I suppose that I have a ring and an ideal, and I can always define filtration like this. So Mn is by definition I to the n times n. Right? So that's a submodule. Clearly, all the three parts of the definition are satisfied. Well, in this case, this is all even work starting with 0. But this still has a special name, so it's called I-adic filtration. Of the module M. And this will be kind of the main example of filtration for us. Okay, definition. again, two parts. Let I be an ideal. So with this ideal, we can define, we can associate the so-called blow-up algebra. So, blow-up algebra. So the notation is BL, where you use I as an index of the ring R. Раздутие. So this is the algebra that used in algebraic geometry to construct blow-ups. So by definition, well, this is just a graded, new graded algebra, which is all the powers of the ideal I. So of course, again, we need to assume that I to the 0 is by definition the ring R. And second part of the definition, so M is a module with I filtration and then we can define the blow-up module, but I'm not sure that everybody would agree with this terminology, but let's still use this notation, blow-up of M depending on the ideal I. And this will be a direct sum of the MNs, where N is greater or equal than 0. So why we need this I filtration in the definition? Well, this is because we can say that this blow-up module is a graded module over the blow-up algebra. I think you can see that you need condition that this is an I filtration to conclude that this is actually a graded module. Okay, proposition. So R is Noetherian ring. R is Noetherian ring. M is a finite R module with I filtration. So then again the following are equivalent, and they have two conditions. So condition 1, blow-up module is finite module of the blow-up algebra. So finite BLIR module. And condition 2, the filtration on M is stable. So this new condition that if you have a filtration and this is stable filtration, using this pair of graded algebra and graded module can be reformulated in terms of something that we understand, namely being a finite module. Okay, so first we suppose that we have a finite module. So this is 1 implies 2. So I want to show that the filtration is stable. So let me define a chain of submodules in the blow-up of M. So Lk is by definition M0, direct sum with M1, direct sum, etc. Then I get to the position Mk, and after that I multiply Mk on the I. So this will be I Mk plus I squared Mk, etc. No, that's clearly a chain of submodules, right? So Lk sits inside Lk plus 1. So since we know that, so what we know, I want to say that there is a stabilization of this chain of submodules. How I can say this? Well, I know that the module is finite, right? I need to understand that now, since blow up IR is Noetherian, right? This is Noetherian. Well, that is because the ring is Noetherian, and the ring is Noetherian. So ideal is also finitely generated. So this whole thing is generated by finitely many elements, namely the elements generating ideal over the R, which is again Noetherian. So this is Noetherian algebra again by the Hilbert spacer theorem.
Yeah, but we have an infinite direct sum here.
Infinite? But that's not a problem. Everything is generated. So you have elements in the I, so in the I there are only finitely many generators, and you can present any other element as products of these elements, sums and products.
Oh yeah, so this is.
So this blow-up algebra is generated by the same elements as I.
Yeah, but I is generated as an ideal, and algebra is generated as an algebra.
Yeah.
But elements are the same.
Yeah.
Okay.
Lk is model is some models of blow M.
Yeah, so the algebra, the blow-up algebra is Noetherian. The module is finite, so this is the module. This is Noetherian. So since this is Noetherian, blow-up I of M is Noetherian. So here I used that this module is finite. So hence there is some n0 such that we have the stabilization. Dun, dun, dun. So there is n0 greater than 0. Ln0 is equal to the n0 plus 1 and etc. And now if you just say look at this identity and look at the corresponding graded components of the Lk, you exactly get what you want. Right? Just comparing the components, will take one component, take component with one index shifted by 1, you get exactly that form. Starting with n0, you get this condition. So this finishes the proof in one direction, that 1 implies 2.
So if graded model is equal, it's equal in every grade.
Yeah, so it means that the corresponding graded components are the same. So 1 implies 2, 2 implies 1. So now I need to show that the blow up of M is a finite module, right? So what we know that Mn plus 1 is I Mn, and this is true for any n greater or equal than some n0. So then I claim that if I consider blow up of the module, this is generated, by the sum I is running between 0 and n0 of the mi. So this is over blow up. Right? So it's enough to consider only several first components, and since all other components you can get by multiplying by something in the ideal I, but ideal I is sitting inside this blow up algebra's degree 1 part.
Should it be blow up algebra?
Yes, thank you. So this condition that the filtration is stable immediately gives that this thing is generated by this finite sum. Well, what we can say now? Well, we can say that R is Noetherian, so M is finite, right? So each of these MIs are just submodules of a, well, it is finite, hence Noetherian, so MI is again Noetherian, so finite. So this thing is the sum of finite modules over R. So the sum is finite R module, hence finite module over blow up. Right? Since the blow up algebra is even larger than R. So if you can generate something using as coefficients elements in R, clearly you can do this for the larger algebra. And that's again the end of the proof, because everything is generated by this submodule, and this submodule is also finite. Okay. So now we have, let me call this theorem, but you can as well call this corollary from this proposition. And in the literature, this has a standard name. This is called Artem, Reese, Lemma in the general form. So as before, we assume that R is Noetherian, M is finite, R module. So finite R module with stable I filtration and we also have L in the M submodule. So then if we set Ln to be equal L intersect with Mn, then Ln is a stable I filtration on L. So essentially, Well, this is chain of submodules. So we define submodules like this, consider the whole chain. The claim, if you start with the stable filtration, you get a stable filtration on any submodule. Well, first of all, of course, we need to check that this chain is actually give us an I filtration. So, right, if we want to show this is an I filtration, well, I think it's more or less clear that this is the chain of the decreasing submodules, since we have this property for the Mn. What we really need to check is that if we take a product of the I and Ln, we can embed this with the Ln plus 1. Well, this is a series of inclusions. Well, first of all, clearly we can embed this into the L and then intersect with the I Mn. Right?
Mn is just filtration, yeah? It's not a grade.
It's filtration, yes.
Yeah, okay.
Do you agree with this inclusion?
Yeah.
Well, we clearly have an inclusion here, since by definition of the Ln, and this is still in the L. So we have this first inclusion. So then the next step is the fact that Mn give us a stable filtration. So this sits inside the intersection of the L and Mn plus 1, which is Ln plus 1. So hence we get the stable filtration. Since we have thus we have an I filtration. So this is an I filtration. Now, why this is stable? Well, the observation is very easy. So you consider the blow-up module for this ideal and the submodule L. So clearly, this sits inside the blow-up of the module M, right? And this even sits inside as the greatest submodule of the blow-up algebra. So being a stable filtration means that this is Noetherian. Submodule of Noetherian is Noetherian. So hence this is stable filtration.
So M is Noetherian.
Yeah, so we have a stable filtration on the M.
Yeah.
We already know by the proposition that this is Noetherian module. So this is the submodule.
Oh, that's also yeah.
So this is Noetherian. Hence the filtration is stable by the proposition. Okay, corollary, a special case of the Artem-Reese lemma. So it says that there is S greater than 0 such that now if you consider the product of the I to the D with the intersection with the intersection you take submodule, intersect with the I to the Sm, and this is the same as the L, intersect with the I to the D plus Sm. And this is for any D greater or equal than 0. So proof is again quite simple. So this is just the case of the filtration, which is I-adic filtration. And then of course there is this D, right? But well, you can just, if you know this for D equal to 1, you know this for any D by induction. So this corollary is just application of the previous theorem to the special case of the I-adic filtration. So now this doesn't use any filtrations, any blow-up algebras. This is just a formula that we proved for any module submodule and ideal. So this is quite famous result in Artem-Reese algebra, Artem-Reese lemma, and it's maybe useful in many situations. So for example, we have the following application of this. So next corollary, this is the gross intersection theorem. So it says the following. You said, well, as usual, you have Noetherian ring, so we have the same assumptions. R is Noetherian, M is finite, and then you said M prime to be the intersection of the I and M. So this is n between 0 and infinity. So then I M prime is equal to the M prime. Okay. Proof. Well, first of all, I to the M intersect with the M prime is the same thing as M prime.
So we want to prove that if you take M prime and
So we want to show, well, we have a submodule M prime. This is even a smaller submodule inside M prime. We want to show that these two submodules are the same. Well, first observation is clear from the definition of the M prime. If this is infinite intersection, if you intersect with one more term, you don't change anything. Now, so let's say this is for M greater or equal than 0. So now let's try to compute I M prime. So I keep I. So instead of the M prime, I'm going to write IS M intersect.
what's IM? Just some module, but how we intersect
It
it
should
is
be IM
M prime.
times M.
Yeah, thank you. So I'm starting the computation of the I M prime. So on the first step, I'm just replacing this M prime using previous observation. Well, I'm just using S instead of M. So on the next step, I use the Artem-Reese lemma to rewrite this as an I S plus 1 M, and then I need to take the intersection with the M prime. So use Artem-Reese lemma, and you're supposed to use when M prime is the L. But again, this intersection is the same as M prime. Okay, so next corollary, which is also called the gross intersection theorem, but now we add some additional assumptions. So if ideal I is sitting in the Jacobson radical of the M, or M prime is faithful, then in this case we can conclude that the intersection of the I and M is 0, so M prime is 0. So this is why it's called the intersection theorem.
What after I sits in Jacobson radical of M, or?
Or M prime is faithful. So the annihilator is 0. So usually in applications, the first condition is interesting. It's not submodule, so this M prime. So you see that the idea is we prove this general observation. Now this looks like a starting point of the Nakayama's lemma. So if you just combine this with the Nakayama's lemma, we can say that the modulo m prime is 0. And hence we get this intersection of all the powers is 0. So this is why it is called the intersection theorem. So the proof. Yeah, so if you know that m prime is a faithful module, that in fact this is a 0 module. So we know that there is x in the ideal I such that 1 plus x applied to the m prime is 0. By the generalized Nakayama's lemma. So if I is the Jacobson radical of the module, then 1 plus x is invertible. Yeah, so if you have one of the assumptions, then we can say that intersection is 0.
Okay, so what we prove? We prove for first
We prove two together. So again, since this is the starting point, this identity, and this is one of the equivalent conditions in the generalized Nakayama's lemma, so I'm using another condition, which is the existence of the x, such that 1 plus x applied to the m prime is 0.
Yeah, but we take I. If we
In the generalized Nakayama lemma, you have three conditions. So one condition is I m prime is equal to the m prime. The second one is the existence of x. So now, additionally, if I know by Nakayama's lemma that if I is in the Jacobson radical, then this thing is invertible, 1 plus x. Hence m prime is 0. So m prime is 0 module. So finally, if m prime is faithful, so if this is a faithful module, it means that all elements that annihilate this module are only 0 elements. This element annihilates this module, so this is 0 element. So x is minus 1, and x is in the ideal. Hence, the ideal is not a proper ideal. That's a contradiction. So it's faithful. Then 1 plus x is 0. X is equal to the minus 1 in the I. Hence, I is R. And that is a contradiction because we assume that I is a proper ideal. And finally, the last restatement of the gross intersection theorem. So notice that I continue to assume that since I use this Artem Reese lemma, everything is Noetherian here. So ring is Noetherian, module is finite, and it's also Noetherian. So intersection theorem is something about Noetherian rings. So I can say that, now let me return maybe to this. R is Noetherian. You take any ideal in the Jacobson radical of R. So then the intersection of all powers of this ideal is the 0 ideal. So that's a property of Noetherian rings. Of course, everything is Noetherian, but I just want to emphasize that this is for Noetherian rings. So maybe as an exercise, you can come up with an example of a ring which is not Noetherian and an ideal in the Jacobson radical, such that the intersection is not 0. Or try to find a counterexample to the statement for non-Noetherian ring. So it looks like we're out of time, right? So we're supposed to finish when? 10 more minutes. Yeah, okay. Okay. So I want to finish with one definition and proposition that we're going to use right now, but we're going to need them later. So again, I is an ideal. So this is ideal. M R module. As before with I filtration. So the associated graded ring is the following graded ring. So this code, well, notation is gr I of the R, and by definition this is the sum over all non-negative n of the in modulo in plus 1.
This is the definition of associated graded ring.
Yeah. You take an ideal. Well, in general, maybe I don't want to use this as part of the definition, but if you return to this general condition where you have just any filtration on the ring, you can say that depending not just on ideal but depending on the filtration on any filtered ring, now you take the sum and you take a quotient of the fnr modulo fn plus 1r. In general, with any filtered ring you can associate a graded ring using this. Now I continue the definition, and I can also, well, this is associated gradient ring, and you can do the same for the module. So the gr I of m. So we assume that on m we have I filtration. So this will be direct sum over n greater or equal than 0 mn modulo mn plus 1. And that's an easy exercise to actually check that this is a graded module over this graded ring.
So, and with stable filtration, then this group model is just finite.
Well, you want to show that there is a proposition which is analogous for the blow-up algebras, right? Yeah, so that's what we're going to do next. So proposition. So yeah, we assume that R is Noetherian. Then gr I of R is Noetherian. Well, in the same way as we've done for the blow-up algebra, and the proof is actually more or less the same. So okay, if R is Noetherian, then gr is Noetherian, and if m is finite, and filtration is stable, then gr im is finite. Finite, of course, as gr ir module. There's only one direction here. But to be honest, I don't know a counterexample. Maybe you can think and come up with a counterexample.
So there can be a group ring the Noetherian, but the first ring is not Noetherian.
No, no. No, for the first part, of course, works in both directions, since the R is what? No, the degree 0 part is R modulo I. So if this is Noetherian, we can say that R modulo I is Noetherian, but we can conclude actually that R is Noetherian.
So it can be also not true in another direction.
Yeah. So that, but the counterexamples might be quite elementary in this case. Something like you take maybe just polynomial algebra and infinitely many variables.
And generated by all the variables.
Yeah, and M is just the maximal ideal with all the variables.
But will it be
Yeah, will be Noetherian. Like,
Yeah, so probably not, because all it will be generated by the I modulo I squared, and this will be infinite dimensional, so it doesn't look to be. Okay, so as I say, I don't know counterexamples. Okay, so the proof of the first part is straightforward. You just, since R is Noetherian, right, you take an ideal. Ideal is finitely generated, so let's give a name for the generators. And then also introduce notation, say xk with the bar. So these are classes in I modulo I squared. So then I claim that the associated graded ring is generated over the R modulo I exactly by these classes. Yeah, so again, you apply Hilbert spacer theorem and conclude this is a Noetherian ring. Prove what?
you said that.
This one?
Yeah. The same as by induction.
Well, more or less, yes. So for me, it looks like it's something obvious, right? So if you just, well, you want to take any element here, right? So, well, it has a representative. It has a representative. Well, in terms of the, well, it can be written as some polynomial in these variables, right? In these generators. So then.
Then this is it. I think.
Yeah. So.
Yeah, but why they can written in x bar, xk bar?
Well, because they can be written in just x1 xs,
Yeah.
and then you take just take them modulo.
Yeah.
Yeah, but you like take the quotient model by in on the I squared, and like I squared always larger than in.
No, I mean, if we have an equality, just ring, we have an equality modulo any idea.
What?
Well, every
Well,
element of I to the power of n can be expressed as a polynomial
Yeah.
in x1 with xn. If you take this equality, this polynomial equality modulo any ideal, your equality still holds.
Yeah, you can say that you have a polynomial. You have for the element you have a polynomial in terms of this axis. Instead of the axis, you plug in x plus I squared, right? And then you kind of open by the distribution, open all the brackets. So then you get some additional kind of summand, and the summand will be in this ideal in plus 1.
Okay.
Okay, so now for the second part. So there is n0 positive such that m n0 plus r is ir m n0. So this is just the fact that the filtration is stable. So hence this is true for any r greater or equal than 0. And now essentially we use the same argument. So looking at this, and well, using the argument as before in the first part, I can claim that the associated graded module is generated by the finite sum. So this summation between n equal to 0 and n0, mn modulo mn plus 1. And the rest of the proof is exactly the same. Right, we start with here m is finite, m is Noetherian, so all these mn's are Noetherian submodules, all the quotients are Noetherian submodules, so this is finite, it will be finite over r modulo I, hence it will be finite over the gr ir. So it's more or less the same as for blow-up algebras. Okay, so we continue next week.